Hi everyone, and welcome to this webinar hosted by us here at Carmenta and Spatial Technologies. I'm Thomas Jonsson Damgaard. I'm a software engineer here at Carmenta. I've been here for roughly 5 years now as a software developer, working on all kinds of different applications, working with customers and working with development here with our different toolkits and products we produce here at Carmenta. And I hope you're all having a great day. This is a short little webinar that is particularly talking about artillery shoot and scoot tactics. This is taking this directly from our presentation at GVSETS this year. It's a ground vehicle systems engineering exhibition that takes place at Michigan Novi over in the States. I'm located here in Sweden, Gothenburg. This is the main office of the Carmenta company. This is where everything started about 40 years ago, so we're celebrating our 40th anniversary as a company. Started back in '85. So yeah, this presentation is all about shoot and scoot missions for artillery units and how we can enhance them using geospatial technologies. And at the forefront of this is of course Carmenta Engine, our core product that helps you visualize and analyze geospatial data. For those of you who joined us at GVSETS, you will notice that this is pretty much the same PowerPoint. I've not made any changes to it. This year was a very special year for us at GVSETS. Not only is it our 3rd year in a row where we get selected for the paper, but this year we also got awarded the best paper in our category of AI and robotics. So that was a very good, nice surprise for us. Very happy about that. So I hope you guys enjoy our little presentation here that I will be doing very closely to the original presentation that I did back on 12th of August 2025 when it took place. That was a lot of fun. So yeah, sorry, not gonna reminisce too much about that. We're just gonna dig right into it. So yeah, let's talk about artillery systems as a start off. I think we're all familiar with how artillery systems work. You throw ammunition at the enemies through cannons. There's a very famous quote by Joseph Stalin, who was not a great guy, just pointing that out, but of course it's pretty obvious. But he's an important historical figure nevertheless, and he reflected upon the battles of World War II, and he said, I quote, "The artillery is a god of modern war," end quote. And the Russians have sort of lived by this motto ever since. Any problem they find, whether it's even real or not, out on the battlefield, they try to solve it using just artillery systems, just hammering the positions. And the reason why they do this is it's a very cheap and cost-effective way to suppress the enemies, which in modern times works perfect for SEAD and DEAD missions, suppress enemy air defenses, destroy enemy air defenses. And so it's very viable, but of course, it's 2025 now. World War II ended 45, so it's been 80 years. So the artillery system have changed a little bit, some modernizations, and many of them are now mobile systems where they are mounted on terrain vehicles. That is really good for maneuverability, survivability. They also have automatic setup for aiming, which increases accuracy, and also automatic reload, which makes them a lot more effective and efficient out on the battlefield. There are a few more challenges for artillery systems nowadays compared to World War II. They are counter-battery radar systems. They see the incoming trajectory of the shells, shells being shot from artillery systems, and then they recalculate the point of origin. And all artillery systems obey the laws of physics, so we can't really get around that. So counter-battery radar systems, that's a mouthful, are quite effective on the battlefield and will unfortunately expose your artillery systems. And there's also, of course, a lot of drones out on the battlefield today, recon drones, attack drones of various sorts, so they can spot your artillery systems and engage you quite quickly out on the battlefield. So artillery systems are still very effective, but vulnerable. So how do we increase their survivability? Well, the idea here is to apply the shoot and scoot tactics, which is a tried and effective method, and we see a lot from the Russo-Ukrainian war. In military terms, you can sort of call it a tactical drive-by, in the sense that you shoot from location area, and then you quickly relocate as quickly as possible to avoid return fire. And this could be, you know, incoming fire from enemy artillery systems, fast movers. It could be, you know, just drones and whatnot. So you just want to quickly relocate to not tank any damage in that sense. And said we take this, we started looking into this particular problem specifically from the studies that we've seen in the Russo-Ukrainian War. This is our third year in a row where we present a paper at GVSETS, and usually the topics are something that we have derived directly from our contacts and our support down in Russo-Ukrainian War. A lot of our systems are used there. Carmenta engine are used in various different end systems of, you know, ground vehicles, combat management systems, etc. So we get a lot of feedback from how the war is going, and we see this sort of shoot and scoot tactics be a very common one to sort of keep your Hauser's fleet alive for as long as possible. And also, a fun fact is that when you relocate very quickly around shooting locations, you also mimic a greater force. If you shoot from multiple locations within 15 minutes, then, you know, the counter battery radar systems, they pick up a lot of bogeys, they pick up a lot of things. You look like a bigger force. So that's a very good side effect of shoot and scoot tactics as well. But it leaves a few questions. When do you shoot? When do you scoot? Where do you go next? What's the mission time window? What's the intensity of the fire? Can you become unpredictable, etc.? There's a lot of questions into the idea of shoot and scoot tactics, and how can we enhance it using geospatial technologies. So we did a lot of research in this area on related work. The first paper we found that was really good was Position Areas by Quinn and Kunkelman. They talked specifically about, you know, how do we quantify and qualify good shooting locations for your artillery systems. Now, of course, this is hardware dependent, so depending on what artillery systems you have, the qualifications will be different. But they had like 5-6 criteria of what a good position area would be for a shooting location. And it's good with everything from, you know, tree lines, do you have vicinity, can you see, the bearing of the ground, you know, the range of which you have with the terrain, is it urban area nearby, you know, road networks, can a civilian spot you, etc. So is it OPSEC in that sense? OPSEC in that sense. So there was a lot of good things. So that gave us a really good insight into what the locations should look like for good position areas. And then we took another look at another paper by Shimon Atkinson, who decided to look into the decision support aspect of shoot and scoot tactics. They created a sort of a support algorithm that is actually based on just a Markov chain, very pure mathematical statistical models that talked about the idea of, you know, when do you shoot and when do you scoot, in the sense that you have a certain success rate of hitting the enemy targets, counter, you know, a risk of being hit yourself. So they worked around with some probabilities of like successful hitting the targets versus, you know, getting a return fire. And then they sort of modeled this with increased complexity. I understood some of the more simplified models they put together, but then they added more complexity to make it more realistic, and, you know, the mathematical aspect just grows in that sense. But a very good paper on decision support. And then we found a very good all-encompassing report by Themis, who ran a lot of simulations, 3D simulations, on you know, how to navigate around terrain and stuff like that for your artillery systems when you engage in shoot and scoot tactics. In particular, he had a lot of interviews with field experts. People have had a lot of experience working with shoot and scoot tactics. They give us some very good insights, like, for example, you know, try not to return to a previously used location, stay outside of its vicinities. You know, it could be drones active in their AO. The enemies can have their instruments already calibrated for that area, so they can engage much quicker. But then there's a few other questions, like maybe you can return to that area a little bit later. You know, sort of the mind games with shoot and scoot tactics. We had a lot of fun. I'll get into that a little bit later on the sort of warfighter, you know, game theory part of it. And I made this sort of into a 3-point triangle to put our paper here in the middle, route networking. That's what this presentation is all about. How do we create this robust terrain and navigational route network for the systems, where we basically, as an input, we're going to take the points that the Quinn and Kunkelman defined in their position areas. They actually presented 20 points in a training facility in Germany. We have extracted those points and used in our simulations. And then we want to create the route network that is needed as an input to the decision support algorithm by Shimon Atkinson. And this route network it's built based on the constraints that we saw from TEMI simulations, and particularly the field experts that he interviewed. So we tried to create a more robust, realistic, good route network based on those constraints. So yeah, now we're gonna just briefly have a overview of the problem, of the area that we're located in and engaging in. So this is a map illustrating our training facility in Germany, our native training facility. And we have two different sections here. We have the top left section and the bottom right sections. In each section you have 20 points, that are position areas for artillery systems. We have given them each a unique label. And for this presentation, I will mostly look at the top left section, but we also had a look at the bottom right, which was more urban environment. The top left one is more, terrain area. That's the area that we really like to work on, terrain navigation and stuff like that. But yeah, I will zoom into this area a little bit, and here we see the different points. And so the problem statement here is that how can we generate a robust route network that gets you from each position only once, one end to the other, in one continuous way, and then back out of this operational area. And how do we solve such a problem? Well, it turns out that this is actually a very common problem in the graph theory, just pure mathematically, and it's actually a traveling salesman problem. Just as the name suggests, it's a salesman that is going through a neighborhood. He knocks on each door only once. You don't want to do it twice, that would be too annoying. And then, after he knocks on the last door, he wants to get out as well. So it's just one continuous tour around the neighborhoods, and he wants to minimize the time it takes to visit every door in that neighborhood. So that's the sort of the problem here. So we illustrate this with one solution that takes 4 hours, 45 minutes, just a non-optimal one, just an example here where we go from each node to the next in one continuous way. But for us, there is a little slight modification when it comes to sort of the risk analysis part of this. And I'll try to illustrate this. So let's say we start at alpha, at A. When we have shot from this location, we do not want to return to this location at any point. That's already solved by the traveling salesman problem. But we don't want to stay within its vicinity. Remember, there could be drones in this area. It could be the enemies could have calibrated their instruments to this area, so they can engage this area very quickly. So we want to actually, when we shoot, we want to get outside of this risk zone, artificially made, but we just want to get out of it as quickly as possible and then get to the next point. But there is a problem, and that is that as we go from one location to the next, we keep creating more and more risk zones. And in the end, we will have created a sort of network, a sort of subgraph of neighboring locations being in direct conflict with one another. Meaning that if I shoot from location Foxtrot here, F, I will be blocking out Charlie, C. So I can only choose one of them. And so the problem actually becomes twofolded. One is, of course, we want to minimize the traveling type as we go around this network. But we also want to maximize the number of shooting locations that we can engage in with this new risk circles added on. And then we call this the cardinal number. The cardinal number needs to be as high as possible, the number of points we can visit with this restriction, while we minimize the total travel time. So it's a twofold problem, and so we have to change our approach to it. And we actually call this the traveling artilleryman problem. So it's an artilleryman that is moving around in the AO rather than a salesman moving around in the neighborhood. So yeah, let's talk a little bit. I'm going to go into some more technical parts right now. I'm not going to try to make it too technical, but the problem here is, how can we solve such a problem? Just pure algorithmically. The problem with TSP problems, traveling salesman problems, is that they are NP hard, non-polynomial. So that means that you can't brute force it, unless you have a quantum PC. So if you have one of those, I would love to play around with those. But yeah, for now we have to assume that NP hard problems cannot be brute forced. So we have to find P solutions, polynomial time-based solutions, heuristic solutions, approximation solutions to these problems. And there are two sets that we try to implement here. The first one is a very greedy, very easy solution, and we call it the nearest neighbor approach. When you go from one location to the next, you rank up all of the leftover locations that are valid. Remember, they have to be outside of all the risk circles that have been generated across the mission. And then you have to just calculate the distance to them in travel time and always select the one closest to you. So it's a very greedy algorithm. And this greediness can be a problem. In this scenario, for example, we start at alpha, we go Bravo, Charlie, Delta, and then at some point we end up in Juliet. But when we get to Juliet, we have completely encircled ourselves. So this algorithm doesn't always work. You cannot, at some point you can end up in a dead end in that sense. So that's why we create, an X-field point, an extra escape leg, and we say that the algorithms are only valid if you can get to the escape leg after having run through the mission. So there's no guarantee that the greedy solution always works, but for some of our tests, it seemed to be working pretty okay. But we weren't, just happy using a greedy solution. We had to use some alternatives, and the one we used is a stochastic approach, meaning we added a little bit of randomization from the stochastic optimization to see if we can find varieties in our solutions. And this is what we call the random neighbor algorithm, where when we select the next neighbor to visit, the next shooting location, we use a bias function to determine based on odds which one we select. So it's not always the nearest one. It could be the next best one or third best one, etc., based on some different statistical models that we used for calculating this bias. And we used 3 different functions here. The only thing you really need to know is that they are strictly decaying statistical models. There's an exponential one, polynomial one, and then a Gaussian one, which is basically e to the power of minus x squared. So they look a little bit different. Now this algorithm is a little bit difficult to explain in words, so I'll just do an example, an algorithm step by step on how it works. So here we have our starting location. We start from alpha, we run the algorithms for a little bit, we go alpha, Bravo, Foxtrot, Juliet, and we end up at Oscar, O. And then the question is, where do we go from here? Well, we have a few alternatives, visualized here in green. There's a few ones like Echo and Charlotte that's already been removed. But I will put them all in a table, and we rank them in the orders of the least time. So Quebec, or Q, is in the top, CR is the next one. And so it takes about 16 minutes, 30 seconds to go from Oscar to Quebec. And the greedy algorithm will just pick Q and won't really hesitate or think twice about it. But then the question is, what will our stochastic algorithm choose? Well, it's random, right? So here I tried to put forward a diagram that illustrates this. In blue, you see the polynomial function working its way. You see the green one is the exponential, and the yellow one is the Gaussian one. And this one is a little bit difficult to explain, but basically, if it's thick or large to the left part of it at Q, it means that it's very likely to just pick Q. So, for example, the exponential one in green, it's very likely to pick Q at the 75% chance. Then we see pretty much a little bit below 20% chance of picking S. So the exponential one is very close to the nearest neighbor, but at certain times, at certain elements, it will select the next best option. And you can take that in comparison to the polynomial function here. It's much more even. So it's very likely to pick one of the top 5 solutions. So it gets a lot more variation, which can give you a lot of funny results, varying results. But so the idea here is that you run the stochastic algorithm for a set of times, maybe 100 or 1,000 iterations, and then you sort of look at different results. Some you will get a lot better, some you will get a lot worse, and then we did a lot of statistical analysis on this to identify, appropriate amounts of calculations you have to do and the time it takes, etc., to find optimal solutions. So if you want to dig more into that, you can have a look at our white paper that we have published on our website, Carmenta.com. Here's just an illustration of what the bias functions, what they look like. And in short, if they're heavy at the top, at the front, That means there's very little variation. If they're more even, there's a lot more variation. So we played around with these to see if, if more variation gives you good results or if less variation gives you better results. So we had a lot of fun playing around with this just to see the different variations. We also noticed that we can do a lot more simplification to reduce the problem, to reduce the computational time, etc. And so when we looked at our problem, we took a real big glance at it and we said, what, the only difference between the TAP problem, so the traveling artilleryman problem, and the salesman problem is this sort of conflict between, selecting one node and eliminating the other one. So what we did was we put all of these nodes together in a conflict graph. So we linked them all together. This turned out to be the Ninja Cat. This was one of the coolest things we found on the paper. So this is a pure coincidence. We get this sort of Ninja Cat with the pointy triangular ears and throwing a kick in the air. I had a good time with this little cat illustration here. Anyways, so the idea is that, okay, so we have a bunch of nodes inside of a graph. They're all connected to one another. Is there a way for us to understand how many of these nodes that we can select independently from one another, isolate them? And yes, that turns out to be a graph problem in of itself. It's the maximum independent set, which is also an NP-hard problem. So you can brute force it. So you have to use heuristic solutions, and we present some of those in our paper if you're interested. But that, in just of it didn't take that much time for us to run a solution on our 20-point problem. Of course, as you scale up the number of points inside of your problem, the complexity or the time it takes to run it increases exponentially. But the maximum independent set is the idea that how many points can I select inside of a graph? These points cannot be neighbor to one another. So in this case, we see the graph here illustrated with alpha and B here, and Bravo. In alpha, the blue dots are the independent ones. They're not connected to the other ones. And then in the B example here, we have 3 blue dots, and just like the other ones, they don't have any neighbors connecting them. So B here is superior to A in that sense. The B is the true maximum independent set. But there's many different ways that you can find it, etc. So it's an NP-hard problem. But if we can find a way to understand the maximum number of independent points we can take from our conflict map, it gives us a few bits of information. It actually tells us, the maximum upper bound of our cardinal number. So we know ahead of time that, in this problem statement for this mission, we know that at best, given the conflict restrictions or the risk restrictions, we know that at best we can do 15 locations here in one sweep without getting too close to one another. So we get an upper limit to the cardinal number, which is really good. And then we also found some very interesting points. The ones that are marked in blue are points that will always be used in an optimal solution. And then we found some points in red. The terminology for this is a little bit vague. We use the so some words in our paper where we call them requisites and I think optionals and stuff like that. But the red ones you can always remove. Basically, they will never be used in any optimal solutions. They're just very poorly placed nodes inside of our conflict graph. So we will always avoid them, which reduces the problem, right? Because you have the original problem where you have to search for 20 points. And if we find 5 points in red that we don't need, we can reduce the problem down to 15. In addition to that, we also know that there's, we have a base solution of 5 points as well. So if you use these 5 points as a base solution, then you can increase the performance even more and get more and more accurate results. So this was a really good sort of simplification, problem reduction, pre-processing phase that was really good and added even better results to our random algorithm, random neighbor approach. Speaking of results, let's have a look at some. This was the solution that we got for our problem statement in the top left corner when we did just basically use the nearest neighbor approach. Nothing fancy here. We got the cardinal number of 10, which turned out to be the optimal one. 10 is the maximum cardinal number for this problem set. And it took us 4 hours to run this mission. Then we compare that to the best solution we got from our stochastic approach. We also get cardinal number 10, which is good. That's the optimal. And now we have a running mission time of 3 hours. We managed to squeeze away 1 hour of mission time, which is very good. Just doing this sort of stochastic optimization, we really tighten these sort of connections between the different shooting locations. So 1 hour less, that's very good. We did the same for the other section with the more urban environment. The nearest neighbor got a cardinal number 10, 2 hour 45-minute mission. We compare it to the best one for the stochastic solution. We got cardinal number 11, which is one more, and a mission time of 2 hours and 20 minutes. So we managed to both increase cardinal number and cut time. So that was really good. And for this problem statement, cardinal number 11 is the maximum one. So it does have some effect where you start in your graph and how you go around, but the exfil point is at least something that you can just put somewhere outside the map and it won't really affect. But where you start in a graph turned out to have some effect to the problems, as we saw in our paper and presented it. But the results seem to be that sometimes the nearest neighbor is really very good, and sometimes the random neighbor can just find much better solutions. That's really cool results. And there's of course a question of how do we know, how optimal we really are. So I just wanted to talk briefly about, how do we know, near optimality when we're using, heuristic solutions rather than pure solutions. So let's assume that we have an optimization problem where we want to minimize some sort of cost and we have a set of constraints. So how do we mathematically try to understand how good of our solutions are? Well, we can create an upper and lower bound. So the upper bound to this problem are any solution that is valid that we can get from our heuristic solutions. They obey all of the constraints, as we saw with our random neighbor. But then we can sort of create a lower bound, a problem that is a bit easier to solve. So we can create a lower bound by loosening some of the constraints, removing the ones that are a little bit difficult. And then we sort of tighten them together and see that this problem is this solution is too good to be true, and this problem is probably not the best. We can find that the true solution is somewhere in between those two. And so for the problem in the top left corner, we try to find a lower bound for cardinality number 10. This one is not very good because it's very loosely put together nodes that are in conflict with one another. So we remove the constraints in the risk circles, and it's not even one continuous path. So yeah, it was not the best lower bound, but we got a cardinal number of 10, of course, and then the runtime of 2 hours 20 minutes. So between this and the best solution we found is about 40-minute window, but we believe pretty strongly that we are closer to the true optimal value with our upper bound limit rather than our lower bound. But there's a few methods we believe that could, possibly improve the solutions a little bit more. Some local search optimization that we propose this in the paper. And then a few future work that we had a look at, just briefly. We add some ideas on how to better the lower and upper bounds on our stochastic or on our heuristic solutions. But keep in mind that when you do that, there's a risk that you add complexity to the problem, which means that the performance could drop significantly. If you're out on the field and you run full-on, physics simulations for your terrain navigations, it will become very accurate, but it will take weeks to run it. So maybe not weeks, but you can sort of get my point that you have to find, the engineering side of it, right? An approximation that is good enough. So we have a few ideas on how to better the lower and upper bounds, but if this is going to be an onboard system and you don't have access to cloud, etc., you have to really think about the performance that you get. So it's a very good balancing. We also had a look at the risk circles that we create. They are strictly binary, either in or out. And we saw that maybe we could have some sort of softly restricted circles to where you optimize, instead of cardinal number, you optimize, the risks that you take versus the numbers that you visit. And then the problem becomes a little bit similar to the one we did last year with the resupply missions, where you balance, risk of being spotted versus, the time to get to the frontline unit as a supply unit, the sort of the balancing there. And then we also had an idea of, should this softly restricted circles, should they also decay over time? If you run a mission for 1 hour, maybe after 1 hour it's okay to return to a previously used one. So there's a few ideas we had also the softly restricted circles, but it will change, the solutions in that sense. But it's an intriguing problem in of itself. We also got some feedback when we sent this paper in for GVSETS. And the idea was that, can you apply game theory to this? What if you optimize this problem so well, the solution so well, that now you become so predictable that the enemies can figure out, okay, these are the optimal positions they would shoot from, and this is the optimal way they would navigate. Well, then, the shoot and scoop missions are completely useless because the enemies can predict that. So can you use, mixed strategy approach, which is something we looked into, can you select, semi-good shooting locations? Can you mix them with some of the good solutions? Instead of selecting the most optimal solutions, can you find some sort of semi-good solutions? And our stochastic algorithm actually comes in very handy here, because based on the feedback we saw that Thomas got from the field experts in his paper, they saw that one of the issues with making these decisions for artillery unit is, where do you go next? Like, where does the commander tell you to go next? And is he truly unpredictable in his decisions? And so the field experts, they gave us this idea that based on the feedback that, can you really get true randomness? And thanks to our bias functions, yes, we can generate true bias or true randomness in our decision here. So instead of selecting the best solution as the stochastic algorithm, the random neighbor one, provides you, select one that is 10, 15, maybe even 20% slower in traveling time. Cardinal number, maxed out, but much slower one. That one will very likely, but no guarantee, be a lot more unpredictable. Could be a lot of fun to play around with, in sort of battle strategy scenarios, war games, simulations. Instead of selecting the most optimal one, maybe you can select one that's a little bit slower, become more unpredictable. Or something that I looked into, maybe you can cut the mission short. Let's say for one problem set, you have the upper bound from the maximum independence set. That at best you could visit 10 locations for this problem set. But what if you cut the mission short to 5? Because those 5s are very close to one another, but just enough apart so that there's not a risk. Then you could run this mission as a sub-mission. It takes much quicker time to run around, and the intensity of the fire is much higher, and you mimic a greater force. So sometimes maybe a good strategy is using, semi-good shooting location, semi-good navigation, route networking, and also maybe cutting the mission shorter instead of using all of them to, so that the enemies don't have enough time to sort of see where you're going, etc. But yeah, that was basically our presentation at GVSETS and for this webinar as well. We had a lot of fun at GVSETS, made a lot of good communication with a lot of people that came over, and of course congratulated us. That was a lot of fun. Being selected as the best paper, that was a lot of fun for me and Mikael who put it together. But just in general, just meeting the community, talking about graph theory and how we can use mathematical tested algorithms and stuff like that to really support the people out there on the battlefield who is supposed to run these actual real missions. How can we support the warfighters and the soldiers in engagements? And it's a very active industry right now, the defense industry, but also a very interesting and very noble industry. How can we put the best tool in the hands of the soldiers? And as a developer in this industry, this is always what we have on mind. How can we make our systems easy to understand, the interfaces easy and not cluttered? How can we balance AI versus the operators? We don't believe the AI will completely replace the operators. I mean, we have movies that predict what happens in the future if we do that, but we want AI to enhance the operators, help them out, give them quick alternatives that then they can select and work with. And so working with Carmenta is a lot of fun on developing those tools. And yeah, so that was a very great show, and I hope you guys found this artillery shoot and scoot tactics interesting, and everything is built on Carmenta engine, right? We use our terrain navigation operator, and it creates a different routes and for different conditions, and then we can use these sort of penalty cost matrices to balance, speed and exposure, visual exposure from the visibility index that you can get from Carmenta engine, etc. And then you can, do multiple navigations, stuff like that sequentially, as in the route planning, etc. So Carmenta engine helps a lot from that standpoint, just like loading in the data, from terrain, from the route network and stuff, but just getting it perfectly set up with this data fusion parts helps a lot working with these papers. But yeah, enough of all that. I hope you guys had a fun time listening to me rambling on this webinar on how to work with shoot and scoot tactics from a geospatial perspective. Of course, I'm not a soldier on the front line, so I wouldn't know how it would be in practice, but just looking at the problem from the studies that we have seen and looking into it, and some of the feedback we've gotten from various sources and from the papers that we have seen, to see if we can help support the operators in various cases. But yeah, with that, I want to thank you all for listening to this webinar, and hope you all have a great day. And if you are interested in questions, you can send them in to us, and we will try to answer them at our support, etc. And it will be a lot of fun listening to the feedback if you guys have any, or if you're interested in using our map engine for their various different applications. There's a lot of use cases out there, and we see just the use cases just expand more and more. You have different sensors today, drones, using them for georeferencing, finding targets, creating new maps, etc. It is a really fun and active industry right now, so a lot of cool things happening. But yeah, I'm not going to drag on too much. I hope you had a good time, and I'll see you all on the next webinar. Have a good one.